Hi everyone, and welcome to this demonstration video for EPiC Grasshopper. My name is Andre Stefan, and today I will walk you through how you can use EPiC Grasshopper to assess the parametric variations in geometry of a typical Australian house and the direct influence of that on the life cycle embodied energy, water, and greenhouse gas emissions of that particular house. So on the left-hand side, we can see in the Rhino viewport a parametric generated geometry of a typical Australian house with live results of embodied energy, water, and emissions generated by EPiC Grasshopper. And on the right-hand side is the EPiC Grasshopper definition. The big chunk over here is the quantification of embodied flows, and typically is a definition of different assemblies that you can see here. Here are the input parameters for generating geometry of the house, and this is how we infer the geometry from these inputs. And this is a quick demo, so we can vary, let's say, the widths and the depths of the house, and we can see directly how this affects the contributions of different assemblies and even then their rankings. I'll just reset that here. A good example to take is the window to wall ratio. So with a 20% window to wall ratio, windows rank fourth in terms of contribution to the total. But let's say we bump it up to, let's say, I don't know, 45%. You can see directly the result on the geometry, and we see now that windows are the top contributor to embodied energy. And so I'll let you play with these this definition yourself. There is a link in the video description to where you can find this file. But what I'd like to showcase here is the integration of such parametrization with the native optimizer within Grasshopper Galapagos. So let's say that you want to now modify the geometry of a house to take a case study and meet certain embodied greenhouse gas emissions benchmarks. So you want to, for example, have something that does not exist, let's exceed, let's say, 500 kilograms of CO2 equivalent per square meter for initial embodied flows, initial embodied greenhouse gas emissions, and you might want to put other targets on the recurrent or on the life cycle emissions. So you can customize this as you wish. These are the current results that are coming from the EPiC analysis here at the back. So we just take them directly and divide them by the gross floor area and send them back to where they need to be. And so let's say your target is 500 kilograms of CO2 equivalent per square meter for the initial greenhouse gas emissions. You go to Galapagos, you say that you want to minimize that. We'll use simulated annealing solver over here. Let's show all the results, even if it's slower, just to demonstrate how that could work. If we start the solver over here, we're modifying just the widths and the depths of the building. And we can see directly how this is being modified here in the Rhino viewport. And we also see how this affects the breakdown of embodied energy directly as well. And so what we're trying to reach here is a zero difference, basically, between the initial greenhouse gas emissions and the actual target value that we have. So I'm gonna speed it up from here onwards by not displaying the simulations in the Rhino viewport and see how that can converge. But already we are quite close. We are at 527 kilograms of CO2 equivalent or below, so 463. And we see that we are not reaching any values that's closer for now with these combinations. So we might have already reached the closest value we can. But that's not really the purpose here. I'm just going to stop the solver and then reinstate that best values that we have found so far, and just press OK. And we see that we reached 527, and that was for this particular geometry. Now, if I go to the largest house and see what that yields, well, that's a little bit better, 524. And this is what we demonstrate in the associated journal paper. So there will also be a link to the description when it's published. And if you're seeing this video and it's already published, well, there should be a link in the video. This also demonstrates that actually embodied greenhouse gas emissions and embodied flows in general decrease faster than floor area as you increase the floor area. And as such, it's easier to reach lower benchmarks per square meters if you just increase the size of your house and do nothing else. While actually this is worse for the planet because you use more materials and therefore more embodied greenhouse gas emissions. So this is just a quick demo to demonstrate that this works with this parametrization, but one could easily think that, hey, I also want to modify other geometric parameters. You might also want to create a range of different assemblies and then put them in lists and then iterate over these lists to identify assemblies that result in the lowest possible greenhouse gas emissions. So sky is the limit, and it's very easy to integrate that into your Grasshopper workflow. But this was just a short video to demonstrate how EPiC Grasshopper can easily be integrated with a fully parametric model and give you on-the-fly feedback about the breakdown of embodied environmental flows and how you can even integrate it with optimizers to identify best-case scenarios. Thanks for watching.